Hello, today's video on StatStax is called Non-inferiority Testing of Standard Deviations. My name is Rick Burdick. As many of you are familiar, in the manufacturing industries, we're often posed with the problem of improving our processes. And one way we do that is we make changes to the processes with the hope that we will improve them based on whatever metrics under consideration. But the one thing we have to ensure is that when we make a change to a process, we have to ensure that we've caused no adverse impact on either safety or efficacy of our drug product. In statistical tools that we have available for comparison, we're often interested in comparing both the average or the mean of the two processes or comparing their standard deviations, which is a measure of variation in the processes. Equivalence testing of means is the tool that we use to compare averages, and you'll find that in Snax video 2. What I'm going to talk about today is the other tool. It's known as non-inferiority testing of standard deviation. And this is what we use to compare the standard deviations. So the statistical test is laid out as follows. If you've seen any of the Snax videos, we've talked about hypothesis testing. And you want to remember that whatever claim you want to make always goes into the alternative hypothesis here. And we say the burden of proof is on the alternative hypothesis. So what we're interested in here is the ratio of the standard deviation of the post-change process to the pre-change process. And I'm using this Greek letter sigma here to represent the true standard deviation of the post-change process, and this sigma with the subscript pre to represent the standard deviation of the pre-change process. Now we form, unlike a difference of means where we look at differences, when we compare standard deviations, we look at their ratios, okay? So ideally, we would like the standard deviation to be decreased in the post-change population. So ideally, we would like this ratio to be 1 or less. However, non-inferiority means that you don't have to have the post better than the pre. It can be somewhat worse. In other words, this ratio can be greater than 1. We just need to ensure it's not too much greater than 1, or that we're not that much worse. So this is the form of the hypothesis, and for K, we choose some value greater than 1, and I've got a table here to show you how we go about selecting that value of K in just a moment. Right now, I've got the formula here, and my reference is the USP chapter 1010, equation 24. What we do now is we take a look at this ratio, and based on a sample of data we've collected from both the post-change and the pre-change processes, we calculate an upper bound, if you will, a worst case value for the ratio of the two standard deviations. So now I'm using the letter S here instead of sigma. That means I've taken some data and I've estimated the value of sigma post with this standard deviation S post. And so I divide it by an estimated value of the pre-change standard deviation. So we take some ratio here. This is called the point estimate. And then I multiply it times some constant here that's greater than 1 based on what we call the F probability distribution. So we're going to inflate the point estimate to take into account the uncertainty of having only a sample available to make our inference. And this will increase the point estimate to, as I said, you can think of it as a worst case value for the ratio. If this value of U for upper, or if this worst case value is less than K, which is my criterion in the alternative, then I can conclude that the method is non-inferior. Selection of K is always the question that people have. What should I pick for K? Well, as I said, you can select a value greater than 1, but you don't want it too much greater than 1. Now, what USP 1010 recommends is you pick K based on the consideration of the process capability of the two processes you're comparing, the pre-change and the post-change. And what this table here shows you in the numbers is the percentage of the post-change process that would be outside 3 sigma specification limits of the pre-change process. And it's actually easier to see if I show you this visualization. Here at the bottom is a pre-change population. I've got it centered at 0. I have specifications, if you will, as these red vertical lines at -3 and +3. So I'm assuming a standard deviation of 1. So 3 sigma specifications would be -3 on the left and +3 on the right. The population that I show above it is a population that has the same mean, centered at 0, but I've increased the standard deviation from 1 to 1.53. In other words, the ratio 1.53 to 1, the value of K is 1.53. If you look at my table here where K is 1.53, you'll see the value 5% here for my out of specification rate. That means the area to the right of +3 plus the area to the left of -3 is 5%. So this gives you a visualization of how much a population post-change versus pre-change would differ given a value of K. The top panel here, I've set K equal to 1.82, so it's expanded the standard deviation. As K goes up, more of the curve falls outside of my red lines, my specifications. And in this case, 10% of the population is here plus here. So the question is, so we have some interpretation, some practical interpretation of what K means. How do we know which value to pick? And it depends on several factors. It depends on how much data you're going to have available. It depends on the risk that you're willing to take of accepting the fact that it's not inferior when it truly isn't. And generally, again, when you plan this type of experiment, you want to bring subject matter experts into the picture so they can also tell us something about values that are acceptable to them. So I'm going to work an example here very quickly. Here's a situation where I have two different analytical procedures. Let's say we're doing a type of bridging study, and I'm measuring the same reference material. So my pre-change here are the blue circles. The post-change are the red pluses. And if we just look at the data, you can see the range on the red is a little bit wider than the range on the blue. My maximum red here is greater than the blue. My minimum red here is less than the minimum of the blue. So we do appear to have greater spread here in our post-change process. Again, that is allowable. We can have greater spread, but the issue is whether that spread is so much greater, it's going to cause us, when we implement the procedure and when we use it in practice, is it going to cause us to have some false signals that say our process or our product is not operating correctly? So to perform the hypothesis test, again, my alternative here, we've got to take the ratio of post to pre of the standard deviations. I'm going to take a 10% OOS rate, which again, I think is generally going to be a reasonable value given the kind of sample sizes we work with on these types of problems. So that means I have to show that the ratio is less than 1.82. You also have to set now a value of alpha, the type 1 error rate, when you calculate the confidence interval. The value of alpha impacts this F statistic that we have down here. I'm going to take 10%. Now, many of you are familiar when you do statistical tests with using an alpha of 5%. I mean, that seems to be the norm. But I will say that when you're doing tests with variances, you have much greater uncertainty than you do when you're testing with means. And testing with means, people typically use alphas of 5%. That's typically the norm if you do an equivalence test of means. But I recommend a higher alpha when you're doing a test with standard deviations, as is the case here, because you've got greater uncertainty. And for a similar sample size that you would use to compare means, you're going to have a much less power with that same sample size when you do tests of the standard deviations. So I'm going to use an alpha of 0.10, sample of 16 in each group. The standard deviation of the pre is 5.5 and of the post 6.5. When I take the ratio, I get a value greater than 1.17. This is the point estimate, okay? We've got to get the upper bound, and so we multiply this 1.17 times this statistical tabled value, the F value, and I'm showing here how you can get that in Excel. It's the FINV function. This calculates the upper bound of 1.65. So my best guess of the ratio is 1.17. Kind of the worst case upper bound guess is 1.65. And now getting this value 1.65, I compare it to my criterion 1.82. 1.65 is less than 1.82, so I've satisfied the criterion. I've demonstrated that my post-change process is non-inferior to the pre-change process, which again is what we hope to do. And in this particular example, if this were a bridging study, I would meet the criteria to replace the present analytical procedure with a new procedure. As a final remark, whenever you do any statistical test, and this is one in particular, you want to perform what's called a power calculation to ensure you have the proper sample size. Both Minitab and JUMP, as I'm showing here, JUMP panel, have programs that will do this for you. If you're not familiar with this, please contact your statistician friends so that you can come up with an appropriate sample size. The reference here is USP 1010, Analytical Data and Treatment. Thank you for joining us. I hope this was useful today.